Hello all, I'm Rajeev Chandran. In today's discussion, I'm going to go through the project that I have created as a part of my course, which is CSCIE 104. The project is called Anomaly Detection for Time Series Data using Neural Networks. So let's begin. The objective of this project is to develop a module for detecting anomalies in the power usage using neural network. Anomaly detection with neural network is formulated in an unsupervised fashion in contrast to a supervised learning, which needs a mapping of features samples to their labels. For this project, I've employed LSTM autoencoders for time series anomaly detection. Now, coming to the data set. The data set for this project has been taken from Kaggle. There is a hourly energy consumption data set which is collected by this organization called PJM Interconnection. The data set contains nearly 16 years of data of several companies. However, for this particular project, I've chosen the only company which is called PJME, and it is based on this I have built my project. Once the data set has been identified, the next step is to actually go through this whole process of cleaning up the whole data set. We need to understand if there are any duplicates, if there are any null values, or if there are any records that needs to be corrected to the CSV format, etc. So as a first step, once you've got the file, we go through this entire setup process, and then we import it as a data frame. So once that's done, then we are in a next step to start the exploratory data analysis to understand how the data is interpret how the data is through visualization. So as the first step, we would take the raw data and then run it through create a plot out of that, and understand the raw data as is. So from that, if you look at this particular plot, you can very clearly see that there is the whole consumption across the years goes in a particular range. It starts at the baseline. There is a 20,000 units of energy which is consumed across. That's the minimum that has been consumed, and as an upper limit, there are it's around 60,000 units, and there can be variations, but it seems to be going in a band, and this across the last 16 years that you see this pattern. Next is to understand the way the data is distributed. From the graph, we can clearly notice that this is a near normal distribution. However, there is a right skewness. With the distribution plot, we should now be able to understand the standard deviations, and with which we will know what would be the percentage of consumption, majority percentage of consumptions in a given year. And we can also notice that the large percentage of consumption is between the 25 and 30k. Thus, you would be able to know how much of minimum units that you would need to produce in a given year. Next, we look at various kinds of pattern. Now, one of the reasons that we are doing such an extensive analysis of the data patterns is to identify what are anomalies. And when I say anomalies, this could be an unexpected usage, a genuine usage, while of course you can also have malicious usage as well, which includes theft and things like that. But going through but doing a plot like this would help you to now get into a minuscule level understanding of how the data is consumed at an hourly level, at a daily level, weekly, monthly, quarterly, season based, and yearly. So with this, you would know what is your normal data, and what are spikes, and if these spikes are genuine or not. Hence, we go through this deep level analysis to understand how the data pattern looks like. So once that we have, as a part of the data engineering, where we also do this feature engineering sides, which helps to do the EDA. One of the other process, which is probably the culmination of the data engineering and feature engineering process, is to split the data into test and train, so that you are preparing it for your data modeling. Now, in this particular case, I have split the data in the ratio of 80 to 20, 80 for the train and 20 for the test. So with this, we would also want to look at how the 80% data and the 20% data look like. From the slides, we can see that it is pretty much alike. So our when we do the modeling, it should not give us any unexpected results. Now that we have done with the data analysis side of it, understood the distribution patterns, etc., we've also pre-processed the data to come up to the stage. We've also segregated the train set and the test set, so that we can start running it in the model. So as a first step, we have to build the model itself. For building the model, I have chosen Keras as my framework, and this is an auto encoder. And I'm using LSTM here, LSTM auto encoder. So in this model, there are 3 hidden layers, and since it's an auto encoder, you'll see that the hidden layers would start at a higher number, and it would decrease and then go back to the higher number. That's the pattern of encoder and decoder. So the hidden layer 1 has 24 neurons, the hidden layer 2 has 12 neurons. Also, there is the regularization layer, L1 regularization layer, and I'm using Adam as my optimizer and ReLU as the activation function. The loss is calculated using MSE, and then we will also calculate the RMSE, which gives the actual percentage of error. So this is the basic design of the LSTM. The next step is to actually run it and then evaluate it. After we have run the model using the training set and then evaluated it against the test set, we can then plot the loss, the training loss against the validation loss. Now from this plot, we can see that there is no significant gap between the training loss and the validation loss, which indicates that the model is good and there is no overfitting. With that, we can then go to the next step of building what to run the data set to understand what are actually the anomalies are. One of the quick ways to analyze that if our model is doing well, and also to know that there are anomalies within this particular data set, is to do this reconstruction of error, plot this reconstruction of error. So what it gives you the difference between the original input data and the reconstructed counterpart of that. So if there are anomalies, then it would not rebuild the anomaly part correctly, thus indicating that there are anomalies in this data set. This plot shows the distribution of the loss which occurred as a part of the reconstruction of your data, giving a good indicator of the anomaly that may exist within the data set. One of the most important pieces of this model development is to calculate the threshold value. So threshold will indicate what is anomalous data and what is not. Now to calculate the threshold, we calculate the mean and the standard deviation of the reconstruction errors, and consider any data points with reconstruction error greater than the mean plus 2 times the standard deviation as anomalous. So we use the reconstruction, that error loss distribution which we saw on the last slide, and use that to build it. So from this plot we can clearly see where the threshold is at this point in time. Now that we have calculated the threshold, it is now time to put the test data into the model and detect the anomalies within that data set. This particular slide shows the plot, which is a plot, and the red color indicates what the anomalies that it has detected within that data set. It also gives you it also shows the sample output of those dates which are anomalous. Hence, we've concluded building this whole solution, starting from the data pre-processing, ending up to detecting the anomaly within the data set. To conclude, with a threshold at 99 percentile, this model that I have developed gave me a precision of close to 97% for the anomaly detection of the data. That's all that I have. Thank you for attending this session, and have a great day ahead. Thank you.